Hello and welcome to Easy Projects. And today it's about the resistor. I have a good selection of resistors here that I can show you, and we'll get into what a resistor is and why we use it. Resistors come in thousands of different sizes, from tiny resistors to very large resistors, and a lot larger than this one. The most familiar type will be this one. This is a 1/4 watt thru-hole resistor, and it is used by a lot of hobbyists to make home projects because it is very easy to handle and it has a decent size. But when making commercial products and stuff like that, these types of resistors are used because they are much smaller and they can be handled by machines. You also get the advantage that the smaller part you use, the smaller your product can be. But you cannot always use these small resistors, and we will get back to why later on. So to understand what a resistor does, we will have to take a look at Ohm's law. Ohm's law says that voltage equals current multiplied by resistance. And you can of course isolate the unit that you want to calculate. So to make this very basic, we can imagine the electricity as a highway. And if we imagine that the volts is the speed limit, you can easily imagine that being hit by a car that drives 6 miles per hour wouldn't feel as bad as being hit by a car that drives 60 miles per hour. And it is kind of the same with electricity. There's of course a bit more to it than that. We can then imagine the resistance as being the width of our road. If we have a road with 3 lanes, we can have more cars getting through than if we had just 1 lane. So we can now imagine the current as being the number of cars that can get through here. This would also mean that if we drive 60 miles an hour on a 1-lane road, say we could get 10 cars to drive through. So if we added another lane or decreased the resistance, we could have 10 more cars, and so on. So this is basically what happens. When the resistance decreases, the current increases, if the voltage stays the same. On the other hand, if we only had the 1-lane highway, I guess it wouldn't be a highway then, but imagine we allowed the cars to drive 100 miles per hour. Then we could get more cars to pass through. So by increasing the voltage and keeping the resistance the same, the current will also increase. But we can also say that if we want to drive, say, 60 miles per hour, and we want to get 40 cars to pass through, then we must have 4 lanes. So the reason why I don't get killed by charging a 9-volt battery is also because of the resistance of my skin. I might, however, get killed if I put my fingers into the outlet, because the voltage is much higher there. So now let's take a practical example of what we can do with these values. So I have this LED here that I want to power, and my power supply delivers 12 volts. So I have to calculate the value for the resistor we will need in order to make this LED run at 20 milliamps. That is the maximum rated current for an LED like this. So if we use our formula from before, we know that 12 volts divided by the current, 0.02 amps, should equal the amount of resistance that we need. And it's saying 600 ohms. And well, that is actually not true for an LED, because there is a fixed voltage drop on an LED, not like the one I talked about before, but we will not go into that in this video. So this value we can expect to be a little bit out. So I got a 680 ohm resistor here, and we'll try to put that in. Like that. I have hooked up an ammeter so we can see the current. And now that we're using a 680 ohm resistor and we didn't take the voltage drop into account, I expect a rather large error on this current reading. Let's try to switch it on. And we're getting 14.5 milliamps. And the LED should be more than happy with that. So now you might wonder what would happen if this resistor was not in place, and we have connected the 12 volts directly across the LED. So why not try that? And before doing this, I removed the ammeter from the circuit. Now let's see what will happen. And as you saw, that just died very fast. But it actually can be much worse than that, and I'll just put a clip in from a previous video I made. So by using the calculations we've been looking at so far, we can calculate that 12 amps will flow through this resistor, because we have 12 volts across 1 ohm. The ground point is at 0 volts. We could also say that we are dropping 12 volts across the resistor. Now what if we have two resistors in series? Oops. And they're both 1 ohm. Now our total resistance is 2 ohms, so only 6 amps can flow through this circuit. So since we can only allow 6 amps to flow through this resistor, there must be some voltage left here. And 6 amps across 1 ohm is 6 volts, so the resistor will drop 6 volts. So at this point you'll have 6 volts. And these 6 volts across 1 ohm will also drop 6 volts, and we're left with 0 volts at the ground point. And you might already have guessed how it would look with 3 resistors. You could add a million resistors and it will still follow this pattern. And if you use different value resistors here, the voltage in the middle will be set by the ratio of the resistance. So all these, except the first one, can be called voltage dividers, because they will divide down the voltage. The only disadvantage with this is that you cannot draw any current from this node. That will affect the output voltage. And of course you probably would not use 2 and 1 ohms, because that will draw huge amounts of current. So it is actually very easy to understand why this voltage will change once you know the theory behind how the voltage divider works. As I said, we're dropping 6 volts across this resistor, and we have 6 amps flowing through it. Say we wanted to draw 1 amp out of this node, then we would need 7 amps to flow through this resistor instead. That will of course mean that we will drop 7 volts across the resistor, and we will only be left with 5. Unfortunately, we cannot use cars to describe this. And now that we're left with 5 volts, we will not have as much energy in this node as we have over here. And of course energy cannot just disappear, so something must have happened. And what has happened is we have dissipated some power in this resistor in form of heat being generated. And when using 12 volts across 2 ohm, that means a lot of heat. Let's take the first example again with 12 volts just across 1 ohm. That means 12 amps will flow through the resistor. And we know the voltage drop across this resistor is 12 volts because we have 0 volts over here. So we can calculate the power by taking the voltage drop across the resistor and multiply it with the current. So that will be 12 times 12. And that should be 144. And that will be measured in watts. Now 144 watt is a lot of power. And this huge resistor, if it is mounted on a heatsink, can take 100 watts. If it's not mounted on a heatsink, it will be about 25 is my guess. And this standard through-hole resistor can take 1/4 of a watt. And if we take an example like this one, here we have a voltage drop of 4 volts. And here we have one of 8 volts. 8 volts through 2 ohms will give us 4 amps. And also 4 volts dropped across 1 ohm will also equal 4 amps. 4 volts multiplied by 4 amps is 16 watts. And 8 volts multiplied by 4 amps is 32 watts. Or 48 watts in total. Now if we take 12 volts across 3 ohms, if we pretend this is one resistor, we will also have 4 amps flowing through it, of course. And we'll have a voltage drop of 12 volts, so we multiply that by 4. And that also gives us 48 watts. So now we have good confidence that this value will be correct. And we can try to do a practical example on the breadboard. So here we have a 100 watt 10 ohm resistor. And I've hooked up a thermocouple so we can monitor the temperature. I have 10 volts across the resistor, so that should give us 1 amp through it. And that should equal 10 watts. So let's try that. And let's see if anything happens. And after a minute it's starting to get hand warm. So now let's try to do the same thing with a 1 watt resistor. And remember, we're still trying to dissipate 10 watts in it. So we expect something to happen. And I don't need to put the thermocouple on there. So let's turn on the power. And something is indeed happening. And you might be able to see it glow. And it doesn't smell that good either. I think I should turn it off. So let's try that again with another resistor, shall we? So that was interesting. Suddenly it just stopped conducting. So that wasn't actually just for the opportunity to destroy something, because it was two different types of resistors. This one, the first one, was a metal film resistor, the one that started glowing and almost caught fire. And now that it's cooled down, we can actually see the metal film inside. And the other one here is a carbon resistor. This is a 1 ohm instead of a 10 ohm, but I just turned down the voltage until it got to dissipate 10 watts as the other one. And this one as well got hot and started to smoke, but it fused and stopped conducting, so it did not do that much harm. I don't know if that's just a coincidence or it's something general for these types of resistors. Well, I guess that was just a coincidence, because this time it just keeps going. It is glowing white hot now. Oh, there it popped. I just upped the voltage a little bit. So I guess it's because this one has a ceramic housing and the other one looks like it's some kind of plastic or something. So this one holds up much better. So that just went a little off topic there, but it was just to show how important the wattage rating is. And you could easily start a fire if you get this wrong, so be careful. And let's just take a look at the schematic symbols for the different types of resistors. Up until now we have been looking at the standard resistor that can be drawn in two different ways. One for America and one for the rest of the world, if I'm not mistaken. And the designator would be an R. This one over here is a variable resistor. It's a two-terminal device where you can adjust the resistance, typically from 0 to a given value. And they are often called VR. And this one might be familiar. That is a potentiometer. And this is a three-terminal device. It's got a fixed resistance between these two terminals, and this arrow is a variable resistance that is basically just connected to a point on the resistor. So if this is a 10k resistor, 10 kilo ohms, and this wiper is at about 20%, that will give us 2 kilo ohms from the wiper to this terminal, and the remaining 8 kilo ohms will be to this terminal. If we move this to the middle, we will have 5 kilo ohms to each side. And if we go back to the voltage drop we talked about before, you might remember I said that the voltage drop is dependent on the ratio of these resistors. So all the voltage will be dropped across both resistors, and in the middle we will have a voltage that is dependent on the ratio. And with a potentiometer we can set this ratio, as I explained before. So we can actually make an adjustable voltage drop, or a voltage divider. Meaning that if we put 5 volts here and 0 volts here, and these resistors are high enough value, let's say 10 kilo ohms in total, then if we turn the pot all the way to this side, we'll have 5 volts at this node, and if we turn it all the way to this side, we'll have 0 volts at this node. And in the middle, we'll have 2.5, and so on. This one down here is a thermistor. That means the resistance is dependent on the temperature. You can get this in a NTC or a PTC type. Negative temperature coefficient or positive. So it will either drop or increase in resistance when the temperature increases. So here we have a thermistor with a nominal value of 1 kilo ohm. It is an NTC type, so we expect it to drop in resistance when we heat it up and increase in resistance if we cool it down. So let's take a look at it. So first let's try to heat it up a bit. And as you can see, it's drastically dropping in resistance. What is it with me and multimeters? They all run out of battery at the same time. So unless we destroyed it with the soldering iron, we expect it to get back to the value we were reading before. And if we were to cool it down, it should increase in resistance. And it does. And this one is an LDR, light dependent resistor. So you might not hear about LDRs very often, but they are actually very cool devices. And as the name suggests, it is dependent upon light. So if I hold it right here, it is about 1.7 kilo ohm. But if I cover it with my hand, it rises to 10 kilo ohms. If I cover it so it's very dark, it climbs to about 140 kilo ohms. And if I shine a torch at it, it's under 100 ohms. And these can be used either as sensors or just resistors. They are used a lot of times to detect when it becomes dark and a light should turn on or something like that. They can be used for a laser tripwire or something. And they can be very fun to play around with. So, I hope you enjoyed this video and that it could be useful in some way. And if you liked it, please give it a thumbs up and subscribe to my channel. So, see ya!